press the bell icon on the YouTube app and never miss another update.
Hello students, welcome back. And today the topic I would like to discuss about the characteristic properties of transition elements. Already in last class we discussed transition elements due to the presence of unpaired d electrons. Due to the presence of unpaired d electrons, they exhibit some characteristic properties. What are the properties? Now we have to discuss. So here the d block elements, properties. Already last class we completed that atomic radii, ionic radii and melting points, boiling points, and one more point is also there, that is densities. These 5 properties already we discussed in last 2 sessions. We have been discussed already, it was over. Atomic radii, what happens, what would be the regular trend of atomic radii, ionic radii and ionization enthalpies and melting points, boiling points and densities. And special characteristic properties. Special characteristic properties due to unpaired d electrons. This will be the reason. Due to unpaired d electrons. Due to unpaired d electrons, transition elements exhibit some characteristic properties. What are the characteristic properties? You consider number 1, variable oxidation states. Variable oxidation states. Transition elements exhibit variable oxidation states. Second one, formation of color compounds or exhibit colors. Transition metal ions, transition metals exhibit colors. Third one, formation of interstitial compounds. Formation of interstitial compounds. And fourth one is preparation of alloys. And fifth one is exhibit magnetic properties, that is a paramagnetic or diamagnetic property. And sixth one is a formation of complex compounds. Complex compounds. And seventh one is last one, that is used as a catalyst. These 7 are the special characteristic properties of transition elements due to the presence of unpaired electrons. Transition elements exhibit variable oxidation states. Transition elements used as catalysis in catalytic reactions. Transition elements transition elements exhibit color properties, colored, and they can form interstitial compounds. They can form alloys. They can exhibit magnetic properties, either diamagnetism or paramagnetism, and they can also form complex compounds. Including with we have to discuss regarding this oxidation states. In that oxidation states we have to discuss about the stability of higher oxidation states and stability of M+2 M couple and stability of M+3 M+2 couple, that electrode potentials. Still we have to discuss the electrode potentials, SRPs, standard reduction potentials, standard oxidation potentials. So electrode potentials which are totally involved in this oxidation states. So these all are the characteristic properties of transition elements. So here first one is variable oxidation states. Transition elements exhibit variable oxidation states. Already we know the transition elements further divide into 4 series, 3D series, 4D series, 5D series, followed by 6D series, and on that series what will be the variable oxidation states? What will be the reason for the variable oxidation states? One and only the reason. What is the reason? Due to the presence of unpaired d electrons. Due to the presence of unpaired d electrons. So here property number 1, transition elements exhibit variable oxidation states. Let us consider 3D series. Before that, what will be the reason means the elements exhibit variable oxidation state due to the involvement of n minus 1 d electrons along with ns electron. Formation of bond participating in bond. Electrons are participating in bond. Which type of electrons are participating in bond formation? N minus 1 d plus ns electrons. N minus 1 d penultimate shell electrons and ultimate shell electrons are involving in the formation of bond. Which electrons? Unpaired electrons. Unpaired electrons only ready to form bond. Number of unpaired electrons is equals to number of bonds is equals to oxidation state. Number of unpaired electrons is equals to number of bonds is equals to what? Oxidation state. Let us consider the general oxidation states of 3D series. Let us consider 3D series. Already we know 3D series scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are said to be 3D series elements. For these 3D series elements, common oxidation state is +2 except scandium. This is point number 1. You make a note, my dear students. Common oxidation state. Common oxidation state is +2 except scandium. Common oxidation state of 3D series. +2 except scandium. Then what will be the remaining elements oxidation states? Already we know that formation of bond. These elements are involving in bond formations, and on that bond formations, which electrons are participating? Penultimate shell electrons n minus 1 d, ultimate electrons ns electrons. If they are available in unpaired electrons only responsible for the bond formation. Pairing also formation of bond, that is considered as coordinate covalent bond. Electron pair donor, electron pair acceptor we observed in complex compounds by acceptors. You observed in complex compounds, that is. So here number of unpaired electrons is equals to number of bonds. According to the bonds, we have to find the oxidation state. So common oxidation state of 3D series. 3D series common oxidation state is +2 except scandium. Scandium +2 unknown. Scandium +2 is not available. Scandium +2 is unknown it is. While coming to the remaining examples, scandium +3 stable, titanium +2 +3 +4, vanadium +2 +3 +4 +5, chromium +1 +2 +3 +4 +5 +6, manganese 2 to 7, manganese 2, 3, 4, 5, 6, 7, iron +2 +3 +4 +6, cobalt +2 +3 +4, nickel +2 +3 +4, copper +1 +2, zinc plus 2. So, my dear students, make a note regarding this. These are the different oxidation states of 3D series elements. So, here what will be the common oxidation state of 3D series elements? Common oxidation state of 3D series element is plus 2. Scandium plus 3, scandium plus 3 stable, scandium plus 2 unstable, unknown it is, scandium plus 2 unknown. While coming to the vanadium, vanadium plus 4 stable, titanium plus 4 stable. Why titanium plus 4 stable? Titanium atomic number is 22, already we should write argon, 4s2 3d2, removal of 4 electrons, then we will get a titanium 4, that is configuration, which configuration it is? Argon noble configuration with 4s0 3d0. Titanium 4 plus stable, scandium 3 plus stable. Why these are stable? Why some are stable? Why some are not stable? Means stability factor is a deciding factor with respect to the half filled configuration or full filled configuration. Half filled electronic configurations, full filled electronic configurations are more stable than partially filling electronic configurations. Clear it is. So, my dear students, make a note. Scandium plus 2 is not exist, scandium plus 3 is exist, and once you observe these different type of oxidation numbers, on the different type of oxidation numbers, maximum number of oxidation states exhibit in 3D series is middle row, just you observe chromium, manganese, iron. Maximum number of oxidation states are exhibited by the one and only element, that is manganese, that is plus 2 to plus 7. Middle of the series means oxidation number increases up to maximum, then it is minimized. So, common oxidation state is plus 2. So, maximum shown by manganese. Where is the manganese position in that element in the series? Middle series. And minimum oxidation numbers are exhibited by left of the series and right of the series. Why left of the series? Means only few electrons are present in d orbitals. In scandium, what is scandium? Already you know that 3d1 configuration, titanium 3d2 configuration. Only few electrons are present in d orbital. Along with 3d1 we should consider 4s2. Here 3 electrons are present, here 4 electrons are present. Only less number of electrons are present. On this less number of electrons, some are participating in bonding. So, due to this, these left portion elements exhibit minimum oxidation states. And while coming to the right portion once you observe, copper plus 1 plus 2 and zinc plus 2 only I said it is. Why? Because of number of unpaired electrons are less, more d electrons means already we know that copper is, we should write 3d10 4s1, copper 3d10 4s1, there is no unpaired, only one unpaired is there, that is 4s1 configuration. Removal of that one electron, what we will get? Cu plus, we will get Cu plus configuration is 3d10 configuration. While coming to the zinc maximum stable oxidation number is plus 2 only. Zinc stable oxidation number plus 2. This is very, very important point. Zinc plus 2 only stable. Zinc plus 1 unknown. Zinc plus 3 also unknown. Only zinc is available in plus 2 configuration, because of on removal of this what you will get here? 4s0 3d10 stable electronic configuration. 4s0 3d10 stable electronic configuration. So, here maximum number of oxidation states was exhibited by manganese, which is present in middle of the row, and minimum oxidation states are exhibited by left of the series and as well as right of the series. What will be the reason they exhibit minimum oxidation states? Due to the lack of d electrons or due to the lack of unpaired electrons. Due to the lack of unpaired electrons or due to the lack of d electrons, scandium, titanium, and while going to the copper, zinc, those are exhibit minimum oxidation states it is. So, maximum given by manganese, and in this manganese plus 7 is maximum, that example is Mn2O7, or one more example also there, that is KMnO4. KMnO4 can be written as MnO4 minus. In MnO4 minus, manganese exhibit +7 oxidation state. Manganese exhibit +7 oxidation state. So 3D series maximum oxidation state exhibit by manganese, that is +7. Manganese, that is +7. 3D series maximum oxidation state is +7. While going to the 4D series, osmium, ruthenium, osmium and ruthenium, osmium OS, ruthenium RU exhibit maximum oxidation state, that is +8. Maximum oxidation state elements, only 2 elements are there. These higher oxidation states are available in the form of fluorides or in the form of oxides. This point keep in your mind, my dear students. Higher oxidation state of transition metals, higher oxidation state of transition elements due to the formation of fluorides or due to the formation of oxides. Here one is OSO4, osmium tetroxide, oxidation number of osmium is +8. RuO4, ruthenium tetroxide, oxidation number of ruthenium is +8. So maximum oxidation state was given by osmium and ruthenium +8. After osmium and ruthenium, while coming to the 3D series maximum oxidation number is manganese, that is +7. Manganese +2 to +7, +2 to +7. As oxidation number increases, oxidizing agent. Oxidation number decreases, reducing agent. Oxidation number increases means oxidizing, while going to backside, reducing agent. Because of these oxidation numbers, which are more stable, which are least stable, can be expressed in the form of electrode potentials. That electrode potentials are completely measured with respect to the enthalpy of atomization, enthalpy of ionization. Enthalpy of atomization and enthalpy of ionization. So these 2 factors was there. Based on that we have to calculate the electrode potentials, measurement of electrode potentials. We should calculate atomization and ionization and lattice enthalpies, some enthalpies which are related to calculate measure that electrode potentials. According to electrode potentials, which is oxidizing agent, which is reducing agent, we have to find with respect to that electrode potentials. So here you should make a note, my dear students. Zinc is stable oxidation, zinc exhibit only one oxidation number, that is +2. Scandium exhibit only one oxidation number, that is +3. And remaining elements exhibit more than one oxidation states due to the availability of N-1 d electrons and Ns electrons. N-1 d electrons and Ns electrons are involving in bond formation. Due to that, they are exhibit more than one oxidation state. Maximum oxidation state was given by the middle series, that is +7 is manganese. Instead of manganese, beyond manganese, maximum oxidation number was given by the 2 elements which are belongs to 4D series. One is osmium, second one is ruthenium. Osmium OSO4, ruthenium RuO4. And here maximum higher oxidation states. Higher oxidation states you found in compounds which are available in the form of fluorides and in the form of oxides, because of more electronegative, small in size of fluorine, more electronegative of fluorine. So easy to accommodate on the central atom. And in some cases here where you found these all are metals. These all are metals, in exception is what means chromium +1 unstable. Here one more copper also exhibit +1 oxidation state. Sometimes the transition elements exhibit 0 oxidation number. Sometimes in some compounds, not sometimes, in some compounds transition elements exhibit 0 oxidation number. Which type of compounds those are means those are said to be complex compounds. Those are said to be what? Complex compounds. Some complex compounds are there, and that some complex compounds they accept electron pairs. They accept from electron pairs from ligands. Some ligands will be there. What are the ligands? Some neutral ligands, H2O, NH3, CO, carbonyl, aqua and amine. Those are neutral ligands. They can donate electron pair because these d orbitals, some elements consist vacant d orbitals. That vacant d orbitals are accommodated by upcoming electron pairs. Upcoming electron pairs means which are donated by the ligands. due to the formation of coordinate covalent bond. On that cases, especially these transition elements exhibit zero oxidation state. What are the examples? Let us consider one example is NiCO4. NiCO4 is called as nickel tetracarbonyl. Nickel tetracarbonyl, or it should be written as tetracarbonyl nickel 0. Tetracarbonyl nickel 0 or nickel tetracarbonyl. In this example, what will be the oxidation state of nickel is? Oxidation state of nickel is 0. Oxidation state of nickel is 0, tetracarbonyl nickel. Or one more example, you consider FeCO5. FeCO5 is iron pentacarbonyl. Iron pentacarbonyl or pentacarbonyl iron 0. Here also oxidation number of iron is 0. While going to one more example, CrCO6. CrCO6 is called as chromium hexacarbonyls. Chromium hexacarbonyl, here also the oxidation number of metal 0. So, nickel iron chromium. Nickel iron chromium exhibit the oxidation numbers 0. Exhibit the oxidation numbers 0. Because these are neutral ligands. So, D block elements exhibit 0 oxidation state. D block elements exhibit positive oxidation states, because all D block elements are heavy and hard metals and heavy and more electropositive elements. Electropositivity is more. Electropositivity is more means generally we expect a positive oxidation state, but in some cases it exhibits 0 oxidation state. This type of compounds are called as complex compounds. In complex compounds, the oxidation state of metal is 0. Not in all complex compounds, only some selected complex compounds. On that selected complex compounds, the oxidation state of transition element becomes 0. Maximum oxidation state was given by manganese, that is +7. While coming to this is a third group, 3B group, 4B group, 5B group, 6B group, 7B group, and these 3 are said to be 8B group, and it is 1B group and it is 2B group. So, here these are the groups which are present in the D block elements. These are situated in the middle of the periodic table. Suppose one more example also there regarding this comparison. Comparison means the oxidation states we have to compare with P block elements. Compare with P block elements means I will give one example regarding this. Before that, you should remember common oxidation state of D block elements +2 only, and scandium +3, zinc +2. Maximum oxidation state was given by manganese +7. After manganese +6 chromium, +6 chromium iron. So, here make a note, my dear students, this tabular form is there in your NCERT text. So, once you observe that values, then you will get idea about this. And some more points are there regarding this oxidation states. So, in KMnO4, manganese is +7 maximum. In K2Cr2O7, chromium is +6 maximum. Maximum +6. K2Cr2O7 potassium dichromate, KMnO4 potassium permanganate. I will give one simple example regarding the stability of oxidation states. Let us consider nitrogen, phosphorus, arsenic, antimony, bismuth. These are 5th A group elements. 5th A group elements. Stable oxidation number is +5, or common oxidation number is +5. Stable oxidation number is +5. Down the group, what you observed, due to inert pair effect, inert pair effect. The stability of +5 oxidation number decreases. The stability of +3 oxidation state is increases. So, heavier metals stable by which oxidation state? +3 oxidation state. What will be the reason? It is inert pair effect. Inert pair effect means reluctance of NS electrons for bond formation. NS electrons are not interested to the formation of bond. They are not ready to formation of bond. Due to that, they cannot split. They cannot split means heavier elements, stability of heavier elements in P block decreases by 2 units. Remember, generally P block 15th A group elements common oxidation number is +5, but down the group the stability of +5 oxidation state decreases, +3 oxidation state increases. What will be the reason here? Inert pair effect. Inert pair effect. Let us consider chromium. Chromium belongs to 6th group. Chromium belongs to 6th group. Chromium, molybdenum, tungsten. Chromium available in +6 state, molybdenum available in +6 state, tungsten available in +6 state, that is WO3, MOO3 and chromium Cr2O3 or CrO3 and CrO3, or we should write one more example, that is K2Cr2O7 +6 +6 +6 +6. What I said here, general oxidation number +5, down the group the stability of +5 decreases, stability of +3 increases. What will be the reason here? Due to the inert pair effect. The reverse trend is followed in this transition, in this group, not only this group, the reverse trend means heavier elements just like as molybdenum and tungsten stabilized by +6 oxidation number, heavier elements stabilized by +6 oxidation number, chromium not stabilized by +6 oxidation number. Due to this reason, chromium +6, which compound in K2Cr2O7, chromium is exhibit +6 oxidation state. This chromium undergoes oxidizing agent, strong oxidizing agent. Strong what oxidizing agent? Strong oxidizing agent, chromium +6 in acidic medium. In acidic medium, Cr is act as a strong oxidizing agent. So, here compare this to this, you have to compare this to this. What will be the difference? In P block, heavier elements stable oxidation state decreases by 2 units. In P block, heavier elements does not stabilized by the group number oxidation state. Clear it is. In P block, heavier elements does not stabilized by the group number oxidation state, but in D block it was reverse. In D block it was reverse means heavier elements stabilized by group number oxidation state, and starting elements not stabilized by group number oxidation state. Due to that reason, chromium 6 in potassium dichromate in acidic medium act as a strong oxidizing agent. Cr2 plus, Cr6 plus, higher oxidation states oxidizing agents, lower oxidation states reducing agents. You should keep this point in your mind, my dear students. Higher oxidation states oxidizing agents, lower oxidation states reducing agents. So, let us consider this example is Cr2O72 minus. Cr2O72 minus is chromium oxidation number is +6, because oxygen -2 into 7 -14, -14 is equals to -2. So, that is +12, +12 by 2 means we will get +6. Already you know this calculation, how to calculate oxidation state, already in first PU all of you know about that. So, chromium in potassium dichromate ion, what will be the oxidation state of chromium is +6, and it is which medium it is? Acidic medium. Acidic medium means H plus. It converted into Cr3 plus. What is the oxidation number? It is +3. +6 to +3 decreases. +6 to +3 decreases. Which reaction it is? Reduction reaction. The species which are involving in reduction is called as oxidizing agent. So, chromium is act as oxidizing, while WO3, MOO3 are not are said to be oxidizing agents. WO3, tungsten oxide and molybdenum oxides are not considered as oxidizing agents. Clear it is. I hope you understood this point. Heavier elements stabilized by +6 oxidation state in 6th B group, but chromium is not stabilized. Due to that, chromium is act as a oxidizing agent in acidic medium, and it convert into +6 oxidation state to +3 oxidation state. +3 oxidation state. Sometimes you found like this equation was there. Cr2 plus gives rise to Cr3 plus. +2 to +3 increases. Reaction, oxidation reaction. Species which are involving in oxidation is called as reducing agent. Here reduce lower oxidation states, reducing agents. Higher oxidation states, oxidizing agents. Higher oxidation states, covalent in nature. Lower oxidation states, ionic in nature. +2 +3 oxidation states, +2 +3, they can form which bonds? Ionic bond. +7 +6 +5, they can form completely what nature it is? Covalent in nature. My dear students, make a note regarding this point also. Higher oxidation states are covalent in nature. Lower oxidation states are ionic in nature. Clear? Higher oxidation states act as oxidizing agents. Lower oxidation states are act as reducing agents. Oxidizing agents as well as reducing agents. So, these are the important points which are related with oxidation states. So, 3D series common oxidation state +2 except scandium, scandium stable oxidation number +3, zinc stable oxidation number +2, and maximum oxidation state was given by in 3D series middle row. That middle row is manganese in 3D series +7, and osmium and ruthenium shows +8. In complex compounds, metals exhibit 0 oxidation number. In complex compounds, metal exhibit 0 oxidation numbers, and in heavier elements, in any group, heavier elements are stabilized by the group number oxidation number. Lower elements are not stabilized by the group number oxidation number, and lower oxidation states are indicates that formation of ionic bonds. Higher oxidation states said that formation of covalent bonds, and higher oxidation states undergoes higher oxidation states are act as oxidizing agents. And here this will be the simple general information regarding this oxidation states. After completion of this oxidation states, let us discuss about the stability of +2 and plus couple. +2 and plus couple means dipositive ion to monopositive ion couple. So, what will be the trends in +2 and plus couple? Trend means we have to already I said measuring of electrode potentials, because of if you know that concept of electrode potentials, according to the electrode potentials you have to find which is act as oxidizing agent, which is act as reducing agent, which can liberate H plus, which cannot liberate H plus. Can liberate H plus is reducing, cannot liberate is oxidizing agent according to the electrode potential values. According to the electrode potential values, those are classified divided into two categories. One is a reduction potential, second one is the oxidation potential. Some potential values are negative will be there, some potential values are positive are there. Positive potential values act as oxidizing agents, negative potential values are reducing agents. According to how they can calculate means they can calculate that electrode potentials with respect to the enthalpy of atomization and enthalpy of ionization and enthalpy of hydration. The sum of the three enthalpies, enthalpy of atomization, enthalpy of ionization, enthalpy of hydration. Based on these three, we have to measure electrode potentials. According to that electrode potentials, which metal act as oxidizing agent, which metal act as reducing agent, which is stable, which is unstable, why this value less, why some elements values negative, why some elements values are positive. We have to discuss now, that is expressed in the form of electrode potentials. So, here next one is electrode potentials. So, next one, trends in M plus 2 M electrode potentials. Trends in M plus 2 M electrode potentials. Electrode potentials can be designed as E naught like this is equals to enthalpy of atomization plus enthalpy of ionization plus enthalpy of hydration. This can be designed by one conversion. Metal solid gives rise to metal plus aqueous. Here metal solid to metal gas, enthalpy of atomization, metal gas to metal plus gas, enthalpy of ionization, and metal plus gas to metal aqueous, enthalpy of hydration. Metal solid to metal gas, enthalpy of atomization, metal gas to metal gas plus enthalpy of ionization. We have to consider starting 2 enthalpies, 2 ionization enthalpies, starting 4 ionization enthalpies. Some different examples are there regarding this, especially to explain the behavior of nickel and platinum. We will discuss later after this. Metal solid to metal gas, enthalpy of atomization, metal gas to metal gas plus enthalpy of hydration, metal plus gas to metal plus aqueous, enthalpy of ionization, metal plus gas plus metal plus aqueous, enthalpy of hydration. So, what will be the total enthalpy? Total enthalpy, this is not E naught, it is enthalpy total. Enthalpy total is equals to enthalpy of hydration plus enthalpy of ionization plus enthalpy of atomization. While calculating these least values can be act as reducing agents, positive values oxidizing agents totally according to the enthalpic changes only, because this is only the simple measurement to calculate electrode potentials. So, here trends in M2 plus M electrode potential. One graphical representation is there, my dear students. This graph was there in your text. According to this graph, it is 0, imagine this is just you have to imagine that only 0.5, 0.5 minus 1, minus 1.5, then you should go a little bit down, minus 1, minus 1.5, and consider it is element titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and finally is zinc. So, these are the 3D series elements: titanium, vanadium, cobalt, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Because already I said that is scandium. Some students said that sir, where is scandium? Scandium plus 2 unstable, already said. Scandium plus 2 not found. Scandium plus 2 not found, scandium plus 3 found. That is very least negative value it is. So, here, and these are what it is? These are electrode potentials. Here electrode potential, standard electrode potential 0 it is. Above 0 act as oxidizing agents, below 0 act as reducing agents. Above 0 elements cannot liberate H plus, cannot liberate H2 gas. Below 0 can liberate H2 gas from acids. Clear? After completion of electrochemistry, you will get a complete idea about this. So, try to understood, because of it is one of the complicated topic. If you are perfect in this, you can do many questions based on this. So, do not lose your confidence, read the concept, then you will get idea about this, clear. So, here this is a 3D series, and in this 3D series imagine this is a titanium, and while coming to this is a vanadium, and it is a chromium, and coming to this is a manganese, and it is iron, and it is cobalt, while coming to this is nickel, we are going like this one, and this is copper, and it is zinc. So, my dear students, connect these lines. In NCERT they was given like this, expected, observed like this, do not get confused. So, this curve was not in a, this curve was not followed in a regular trend, it is. Once you observe this curve not followed in regular trend. Once you observe in this example, one and only copper, the electrode potential value. The electrode potential value of copper is 0.34 volts. Make a note, my dear students, this is very important point. The one and only element, that is copper, electrode potential is positive. Electrode potential of copper is positive. Remaining all elements which are present in 3D series, electrode potentials are negative only. Electrode potentials are negative. So, based on this information, copper cannot liberate hydrogen gas with acids. Keep this point in your mind. Because of copper electrode potential value, positive value. Positive values are act as oxidizing agents. Negative values are act as reducing agents. Positive values are act as oxidizing. Negative values are act as reducing agents. Based on this, you should make a note regarding copper. Copper electrode potential is positive value. Copper cannot liberate hydrogen gas with acids. Suppose copper combine with acid, copper combine with concentrated nitric acid, copper combine with concentrated sulfuric acid, then not expect hydrogen. Instead of hydrogen, they can liberate some more gases. Already one equation also you know, that is copper plus dilute HNO3. Copper plus dilute HNO3 gives rise to copper nitrate plus NO. What is NO? NO is called as nitric oxide. Copper with dilute HNO3 gives rise to nitric oxide. Same copper with concentrated HNO3. Copper with concentrated HNO3 gives rise to same compound CNO3 taken twice plus NO2. NO2 means nitrogen dioxide. Nitrogen dioxide gas liberate, nitric oxide liberate instead of hydrogen. What will be the reason? Means copper electrode potential value is 0.34. 0.34 means positive value. Why? What will be the reason? What will be the reason for copper electrode potential positive? Because of Cu solid to Cu2 plus aqueous. Cu solid to Cu2 plus aqueous, the energy is not sufficient to convert copper solid to copper 2 plus aqueous. The enthalpy of hydration is not supporting. Due to that reason, copper electrode potential is 0.34. What will be the reason? Means you should make a note here: low enthalpy of hydration and high enthalpy of atomization. These points are very important, my dear students. Low enthalpy of hydration, high enthalpy of atomization. To conversion of copper solid to copper 2 plus aqueous is very difficult, more energy required. that energy is not available from enthalpy of hydration. Due to that reason, copper is not liberate hydrogen gas with metals. Suppose copper reacts with metal, copper is not liberate hydrogens with acids. Suppose copper reacts with acids, those are concentrated sulfuric acid or nitric acid, that acids undergoes reduce. That acids undergoes what it is? Reduce. So, copper is a good oxidizing agent and the electrode potential value is plus 0.34. Only unique behavior of copper, copper only special. Remaining once one table was there in your NCERT text. Once go through the table, M2 plus M coupled table, M2 plus divalent versus metal coupled table you observed. On the table, one and only unique behavior copper is plus 0.34, plus 0.34. Remaining all elements negative values only. Remaining all elements negative values. And here some special points will be there regarding this graphical representation. While coming to titanium to vanadium to chromium, this graph will be slightly increases. After that chromium to manganese decrease, more negative, chromium to manganese more negative, cobalt to nickel more negative, copper to zinc more negative. Keep these points in your mind. Copper to zinc value more negative, and compared to cobalt to nickel more negative, and chromium to manganese more negative. What will be the reason for this? What will be the reason for this means you should remember zinc electrode potential minus 0.76 volts, zinc electrode potential minus 0.76 volts. While coming to the nickel, this is zinc electrode, and here while coming to the nickel electrode potential minus 0.25 volts, minus 0.25 volts it is a nickel electrode potential, and manganese electrode potential minus 1.18 volts, minus 1.18 volts, this is for manganese electrode potential. So, you should make this like this, then you will get idea about this, like this, okay. So, what will be the reason why these are more negative? Manganese, zinc are more negative and nickel also more negative. What will be the reason? Manganese plus 2, zinc plus 2. What is manganese plus 2? Manganese plus 2, Mn2 plus configuration 4d0, 3d5. 3d5 stable electronic configuration. Manganese which configuration it is? 3d5 electronic configuration. Next coming to zinc, zinc atomic number 30, 4s0, 3d10. So, here also 3d10 configuration. Electrode potential values of manganese and zinc more negative. What will be the reason? One and only the reason is a stable electronic configuration, d5 configuration in manganese, d10 configuration in zinc, d5 configuration manganese, d10 configuration in zinc. So, electrode potential values are more negative, and electrode potential value of nickel is more negative than adjacent. What will be the reason means enthalpy of hydration, enthalpy of hydration is more negative to nickel. So, what is the reason here? More negative of enthalpy of hydration, more negative of enthalpy of hydration, more negative of enthalpy of hydration takes place in nickel. How you have to calculate more negative of enthalpy of hydration means according to the ionization potentials. Successive ionization potential values are there in your table, tabular form. I think in the table it is 8.2 or 8.3, one table was there in that NCERT. So, go through that NCERT, successive ionization potentials, starting to ionization potential values are what? Then you have to calculate that average, compare with others. So, we will get different because of while this conversion solid to gas, gas plus to aqueous takes place in different forms, because different metals are available in different crystal structures, CCP, HCP, BCC, different crystal structures was there. Due to that reason different type of ionization enthalpies, different type of enthalpy of hydrations variations takes place. So, in this example, in this in this graph you should remember 4 points: stability of M2 plus, M couple electrode potentials. So, in this one scandium is not there in this series because scandium plus 2 is unstable. So, removal of the scandium, while next remaining elements titanium to zinc. One and only unique behavior of copper, that is plus 0.34 electrode potential. Copper is act as oxidizing agent. Copper cannot liberate hydrogen gas with acids. That point you keep in your mind. What will be the reason? Low enthalpy of hydration and high enthalpy of atomization. Why high enthalpy of atomization? Copper solid is converted into copper 2 plus aqueous, much more energy required. Transformation of solid copper to aqueous 2 plus, much more energy required. So, sufficient enthalpy of hydration was not there. So, due to that reason, low enthalpy of hydration, high enthalpy of atomization, copper unique behavior, positive electrode potential value plus 0.34. Next, coming to next elements, some special cases are there. That graph is increasing at a particular point, that graph becomes decrease. Why it was decrease? Manganese and nickel and zinc. What will be the what was the perfect reason regarding more negative electrode potentials of manganese and zinc means due to the D5 configurations and D10 configuration. D10 configuration in zinc and D5 configuration in manganese. And what about the reason for nickel means nickel is more negative enthalpy of hydration. More negative enthalpy of hydration can be calculated in the form of average ionization enthalpy, starting to ionization enthalpies. Starting to ionization enthalpies, based on this we have to decide the more negative enthalpy of hydration. So, due to that reason Na2 plus these all are act as reducing agents, it is Cr2 plus act as reducing agent, Mn2 plus reducing agent, Mn3 plus convert to Mn2 plus oxidizing, 2 plus 2 3 plus reduction, reduction means oxidizing, oxidation means reduction. So, species which are involved in oxidation is reducing agent, species which involving in reduction is oxidizing agents. So, my dear students, read this concept in your text. I hope you understood. Read it twice or thrice, then definitely you will get idea about this. And after this, next trends in M plus 3 versus M plus 2. M plus 3 versus M plus 2 trend we have to discuss next class, and followed by stability of higher oxidation states and halides and electrode potentials. After that, remaining properties we will discuss. So, I hope you understood. All the best, stay safe and be happy, be confident. Thank you.